Please watch these videos first. Done? Then let's go. Recall zeroth law of thermodynamics, which is tell you that if there is thermodynamics equilibrium, then the temperature for system A equals to temperature for system B, and so on. If there is system C, then system C has same temperature too. Here, what is temperature? Temperature here is about thermodynamic state, so here we can quantify hot and cold not just by sense, as microscopic sense, but as quantity. And the other interpretation is about energy that relate to molecular, and then we have particle and molecule, of course, which is in microscopic sense. So by this sense, we get thermal expansion phenomenon explained. And here's the thing. This law restricts only for final state, or we just say thermal equilibrium. So the question is, what governed before it? Here, we start the journey to all the law of thermodynamics such as first law, second law, and third law. In this video, we only discuss about first law. As a disclaimer, first law and second law found first and the zeroth law. So after we find out about thermal equilibrium that quantify temperature, we send thermodynamics equilibrium law as the zeroth law that is more specific and fundamental than first and second law. Okay, then let's recall about Newton's law video about motion. In that video, of course my old videos, we just discovered about energy conservation, but for isolate system, or there is no energy or matter out, which is in this illustration. We have an object in white, the floor with yellow, and the boundary of system with red. That here, this white object one out of red border and the energy one out. So here we want to generalize this by using thermodynamics law. Here, imagine we have S as closed system, which is no matter out but energy can. Then we can give mechanical and thermal disturbance as energy. So by mechanical part, we can compress, shear, stretch, and etc. And by thermal disturbance, by difference of temperature, or here we know as heat transfer, which for mechanical defined as delta W here, or delta W, and for heat transfer we define as delta Q here, which can flow through in and out. By this expression, we can infer that heat is energy, so Q doesn't necessarily equals to temperature. And here, the first thermodynamics law has its role. Next, we set this illustration down and we're adding some label here that delta W can go in or go out. Here, if we want to define what first law of thermodynamics, let's say the internal energy difference by the work and by the heat transfer can create the difference of internal energy due to W and Q is about by closed system, delta U plus delta W is equals to delta Q, which here delta W will greater to 0 when S a system do work and less than 0 when S get work from external. And here delta Q greater than 0 when S get heat and less than 0 when S lost heat. And the last one for delta U is about difference of internal energy that may vary because of its composition or internal characteristics in S, which we learn in Newton's law. So then, these two definitions about delta Q and delta W come from external disturbance. And here's some note. Delta W relate to work, which in classical mechanics we define as this integral that F is force to system and ds is about shift of system. But in first law of thermodynamics view, the difference of volume is a shift now, not ds. So for dimensionalization, P relate to force or about thermodynamics pressure, so mostly in literature, delta W is equals to P multiplied by infinitesimal difference of volume. Next, about delta Q and delta U These two will relate to difference of T, which delta Q here we will discuss in second law of thermodynamics, but mostly delta U commonly relate to difference of temperature or delta T. And next, we note that for isolated system, the difference of U is equals to 0. So by first law, we get that delta W is equals to delta Q, which delta W we can interpret as kinetic difference, and the delta Q is about dissipation of internal system. This result is what we got in Newton's classical mechanics. Next, there is isovolumic or isochoric, which is this system has difference of volume equals to 0. So by what we defined before, delta W will equals to 0. So as next consequence, delta U will equals to delta Q. Next, we have isobaric system, which is delta P or difference of thermodynamics pressure is equals to 0. This condition may helpful in future videos. And the last one, we have adiabatic system when delta Q is equals to 0, or we can roughly speak as no heat transfer and has consequence that delta U will equals to minus delta W. Or in classical mechanics, this is a system without dissipation. These four cases, a special case shows in first law in most literature and most classical thermodynamics problem. Until this section, we noticed that energy can flow to anywhere, anytime. Okay, that's cringe. Okay. Anyway, this statement, including that heat can transfer from cold to hot, which is violating empirical observation, and the second one, it can flow from future to past because of time translation, some kind of symmetry, and of course, it's violating empirical observation. These two considerations will be our discussion in next video. And that's the definition and some basics to understand about first law of classical thermodynamics. I hope you enjoyed this video. If you like this video, don't forget to share and subscribe. If you have any questions, please drop comment below. And that's it. See you later.